This video is produced by Sammy and
Kevin Burgess
for by Inquisition Press to support the workbook Sophomore Organic Chemistry 1 by Inquisition, available from www.byinquisition.org.
So, Sammy, pop quiz. Who were Brian, France, Weymouth, Harrison, Eno and George?
I'm really not sure.
Probably before you were born. These were the talking heads. You heard of them?
No.
No? Never?
No.
Oh my god, you make me feel old. Okay, if we displace chlorine, it displaces as
Chloride.
Chloride, yeah, good. And if we have an ammonium salt, then the charge on the leaving group is
Neutral.
neutral, yes. So we could add an anion, we make a neutral species, and we make a neutral species leave. So I call that charge balance, because you add an anion to a cation, and the net charge is nothing, and you generate neutral species. In SN1 reactions, the slow step is loss of the leaving group to give you a carbocation. Slow loss of iodide, or bromide, or chloride, or acetate even. Mesylate, remember, is the leaving group. Allyl tosylate, or if I took an allyl hydrogen phosphate, we'd lose hydrogen phosphate anion, or dianion I should say, by again breaking this charge and generating a carbocation. Now it's not nice to make OH into a leaving group, correct?
Mm-hmm.
So what do we do to it first?
Protonate it.
Protonate it. And when you protonate an OH and make it leave by breaking the bond adjacent, you generate a
Neutral species.
neutral species, which is water. And the organic part is a carbocation. Okay, so you could represent that. In this funny example here, the protonation occurs on O1, because remember, when you protonate on O1, the lone pairs from O2 can push in and quench that positive charge by resonance. Whereas if we protonated on O2, couldn't make that happen. Okay, so once we've got our carbocation, adding an anion is just a one arrow push. Do you start from the cation, Sammy?
No.
You start from the
Anion.
anion. Good. And if we add an anion to a cation, we will get
A neutral charge.
neutral, no
Which is
charge
no
at all.
charge, yes.
Yeah. We could lose chloride and attack with an alcohol, in which case we have to deprotonate afterward. Allyl chloride, loss of chloride, attack with alcohol, deprotonation gives us the product. If we have this center here between two aromatic groups, loss of chloride, is that easier or harder than if it was between two methyl groups?
Is it easier?
Easier, because the cation is more stabilized.
Yes.
Yeah. And the nucleophile here, just for a change, is an amine, adds and then loses a proton to give you the tertiary amine product. Trityl chloride, is it good or bad for SN1?
It's very good.
Yeah, it's one of the best. So just heat it up in water, the chloride will leave, and water adds, we get an alcohol. Similarly, allyl systems, are they good or bad?
Also very good.
Very good, yeah, because the carbocation that's left behind is stabilized. And alcohol, we could protonate that, make it leave, but loss of water is,
The slow step.
yeah, and nucleophile then comes in.
Quickly.
Yeah, so if you were in a hurry to go home and you added extra nucleophile, would it help you?
No, wouldn't,
No.
because that's not the slow step.
That's right, the rate determining step is the one where you lose water. Good, so Sammy, in the energy diagram, how many humps on the camel, Sammy?
3.
Okay, so the rate is proportional to the substrate concentration and it's equal to a constant times that substrate. Let's think about carbocation stabilities. If the carbocation is more stable, will that increase or decrease the rates of SN1?
It would increase.
Because the slow step is facilitated, yeah. So if I take tertiary, primary and secondary alcohols, it's the tertiary ones that react fastest and the primary ones will react slowest. Similarly, if I take alkyl halides, tertiary bromo is faster than secondary bromo. Primary iodo is faster than primary bromo. If you're comparing two primaries, then look at the stability of the leaving group. We can use these 1 degree, 2 degree, 3 degree for carbocation, primary, secondary and tertiary, and indicate the stability. The least stable is primary, to tertiary. The rates, substrates will give you primary cations react slower than those that will give you tertiary cations. Now, in assessing the stability of cations, as we've seen before, it's the sp3 orbitals that can tilt a little bit towards the empty p orbital and stabilize it. So the more p orbital stabilization from sigma bonds you have, the greater the stability of the carbocation. So that's why ethyl is more stable than methyl as a carbocation. And that's why also T-butyl is more stable than the T-butyl carbocation. In terms of stereochemistry, the carbocation that you get from an SN1 reaction, is it tetrahedral or is it flat?
It's flat.
Because it's what hybridized?
sp2.
sp2, good. sp2 is flat, planar, 120 degrees. So this center here will be lost, and so when you add a nucleophile, you will get a mixture of diastereomers. Good, yeah, because that other chiral center doesn't change. But in this case, if we take an antimerically pure and do SN1, we will get a racemate. We'll get 50-50 because the nucleophile will add to both bases. Now, in this funny one here, is this a chiral molecule?
No.
No, because it's got a plane of symmetry, yeah. But you will get a mixture of products. Can you describe them? There will be cis and trans, actually. But they're still not chiral. And how about this one? Will I get cis and trans there?
Yes.
And because this one doesn't change, I don't lose all the optical activity. This one doesn't change, so I get a mixture of diastereoisomers, which are also cis and trans isomers.